Hello, welcome everyone. In today's lecture, we are going to look at failure theories, and specifically, we will look at failure theories for brittle materials. Okay. So by the end of this lecture, essentially what you'll be able to do is calculate the safety factor for brittle materials using what is called as a maximum principal stress theory. Okay. But before we get into the failure theory of brittle materials, we just want to have a little bit of a background. Okay. So how do we define failure of materials? Okay. So first thing you need to know is that materials can fail mechanically under static conditions or dynamic conditions. So static conditions means essentially the load is constant, or in the case of dynamic conditions, the load is variable. For example, when you have fatigue, the load can be like changing in a sinusoidal manner, or it could be changing over time. So essentially you can have constant load for some time, then you have no load, then you can again have constant load and so on. So essentially it is a time varying condition. Okay. And other forms of dynamic conditions can include impact. Okay. So we are not going to look at those conditions in which materials fail. So we are only going to look at failure of materials under static conditions. Later on in the class, we will look briefly into fatigue failure, okay, and you will be able to know a lot more on fatigue failure when you take your design class. Okay, so that is what we're going to do it. And the second thing that I want to kind of talk about a little bit before we look into the failure of materials is that we should distinguish between brittle and ductile materials. Again, you have already seen this probably in your solid mechanics class. So brittle materials are materials that usually have a strain to failure of less than 5% or 0.05, okay? And there are lots of examples of brittle materials. Glass is one example, ceramics are another, concrete is another. So all these materials essentially can't take much deformation, especially when you apply a tensile load, okay? On the other hand, ductile materials are typically classified as materials which have strain to failures of more than 5%. Sometimes this could be much larger than 5%, 20%, 30%, or even 50%. Okay? And typical examples of ductile materials are metals and metallic alloys and so on. Okay? So we use both of these kind of materials in engineering, and that's why we need to look at the failure criteria for both brittle materials as well as ductile materials. Another important difference between brittle and ductile materials is how we define failure. Okay? For brittle materials, failure usually means fracture. So essentially the material splits into two or more parts. Okay? So that is what failure usually means. But for ductile materials, failure can mean different things. So one way you can say that a ductile material has failed is if it deforms permanently or it deforms plastically. So essentially if you take a piece of copper wire and then bend it, right? If it stays in that bent position, it means that it has undergone some plastic deformation. So it has permanently deformed. Okay? So that can be considered failure in some cases. In some cases, you can tolerate plastic deformation. What you don't want is actually actual breakage or fracture. So in those conditions, you will say that this material or this part fails if it actually fractures. Okay? So for ductile materials, you can look at both plasticity as well as fracture as failure criteria. For brittle materials, usually it means just fracture. In this particular class though, we will not be focusing too much on the fracture of ductile materials. We will mostly be looking at plastic deformation or yielding of ductile materials. As far as brittle materials are concerned, we will be mostly looking at fracture. Okay. So again, before we go into the actual maximum principal stress theory for brittle materials, the first thing that I want you to know is that the brittle materials are a little bit different from ductile materials in the sense that their stress strain response during a tension experiment is often very different from the stress strain response during a compression experiment. So if you take a brittle material, say something like concrete, and then try to apply a tensile deformation, what you will see is that it will fail at very, very slow strains at very low stresses. So if you think of this as your stress strain curve during tension, it essentially is linear, which means that it is elastic pretty much till the point of failure. Okay, so it elastically deforms, and there's probably a little bit of plastic deformation or nonlinear deformation, and then the material fails there. Okay, the main thing to note is that the strain to failure, okay, epsilon f, is very small. Usually it's no more than 1 or 2%. Okay? And the stress to failure, okay, which I call as SUT, which I mean as ultimate tensile strength, UT stands for ultimate tensile strength, that is also fairly low. Okay? So essentially, if you take a brittle material and try to apply tension, it fails at very small strains and at fairly low stresses. On the other hand, if you take the same brittle material and now compress it, it can take quite a bit more stress. Okay, again, the response is more or less linear until failure. There is not too much plastic deformation. But the value of SUT or SUC, which is the ultimate strength in compression, okay, is quite a bit larger than SUT. Okay? For something like concrete, the compressive strength can be 5 times larger than the tensile strength. And that is the reason why you try to have concrete beams in compression, not in tension. So essentially, when you have a structure and you have a concrete beam, you usually have that concrete beam under compression because it can take a lot more stress under compression. Okay? And that's why when you have a concrete beam that goes across, you reinforce it with steel so that the steel can take the tension. Okay? So that's the reason why you always try to subject brittle materials to compression rather than tension. So this is something that you must keep in mind. So the ultimate compressive strength is quite a bit larger than the ultimate tensile strength. So here, when I say SUC and SUD, I'm just referring to the absolute values. Okay? Of course, compression means the stress is negative, but the compressive strength itself, what I mean by that, is the absolute value of the stress at which it fails under compression. Okay? So this is something that is important to know, that the compressive strength and tensile strengths are different for brittle materials, and the compressive strength is quite a bit more than the tensile strength. Okay. Now, given that we know this, then we can look at what is the maximum principal stress theory for the failure of brittle materials. This is one of the simplest theories that is out there for predicting the failure of brittle materials. And the theory simply states that brittle materials fail when the maximum or minimum principal stress exceeds a threshold. Okay? So one thing that you must keep in mind here is that we are not talking about just normal stress, we are talking about the principal stress. Okay? So essentially, you know at this point how to calculate principal stresses at any point. Okay? So if the maximum principal stress or the minimum principal stress at a particular point exceeds the threshold value, then you will essentially have fracture starting from that particular point. Okay? Now, to kind of visualize it a little bit better or kind of understand it a little bit better, let's just consider a simpler case where you have a 2D stress state. Okay? So when you have a 2D stress state, you have only two principal stresses, okay, sigma 1 and sigma 2 that you need to calculate. The third principal stress is 0. Okay? So let sigma 1 and sigma 2 be the two principal stresses or the non-zero principal stresses. Okay? Then in that case, the factor of safety n is defined as follows for the following three cases. Okay? So case 1 is basically where you have both sigma 1 and sigma 2 to be greater than 0. Okay? Both the first principal stress and the second principal stress are greater than 0. Okay? In that case, your factor of safety is just defined as SUT over sigma 1. Okay? Again, remember, sigma 1 is the first principal stress, so it is always larger than sigma 2. Okay? So in that case, your factor of safety is nothing but SUT over sigma 1. Okay? And of course, if your sigma 1 exceeds SUT, your n will be less than 1, which means the material will fail. Okay? But in the case where sigma 1 is less than SUT, then the factor of safety is just given by SUT over sigma 1. Okay. Now let's consider the second case, okay, where sigma 1 is greater than 0, but sigma 2 is less than 0. Okay? Again, sigma 3 is always 0 in this case because it's a 2D stress state. Okay? Now, if that is the case where sigma 1 is greater than 0, but sigma 2 is less than 0, then you have to evaluate n in two different ways. Okay? So the first way you evaluate n is SUT over sigma 1. Okay? So SUT is the ultimate tensile strength. Divide that by sigma 1. That gives you one value of n. For the other value of n, you essentially consider sigma 2. Okay? And you essentially calculate n by minus SUC over sigma 2. And the reason that you have a minus sign is because when you say SUC, you're only looking at the absolute value. But sigma 2 is obviously negative. So a negative of a negative becomes positive. So n has to be a positive number. Okay? So what does it essentially mean? This maximum principal stress theory essentially states that, okay, if there is a point in the material, okay, and it has a principal stress that is positive, or sigma 1 is positive, if that sigma 1 exceeds this SUT, it will fail. Or if it has a sigma 2 which is negative, and if that sigma 2, the second principal stress, is larger in magnitude than SUC, then the material will fail. Okay, so essentially, if the tensile principal stress exceeds a threshold, or the compressive principal stress exceeds a threshold, which is SUC, then the material fails. Okay, so now if you look at case number 3, you have both sigma 1 and sigma 2 are negative. Okay, both the first principal stress and the second principal stress are negative. Okay, and we know that sigma 1 is numerically greater than sigma 2. Which means that if both sigma 1 and sigma 2 are negative, then the absolute value of sigma 2 will be greater than the absolute value of sigma 1. Okay? So essentially, in some sense, you can think of it as sigma 2 is the bigger compressive stress. Okay? Then in that case, of course, this bigger compressive stress is what matters for determining the factor of safety. So if n is now defined by minus SUC divided by sigma 2. And if this value is less than 1, the material will fail. So for the first case, n is very simple, SUT by sigma 1. For the case 3, it's again simple, n is nothing but minus SUC divided by sigma 2. For the second case, where sigma 1 is positive but sigma 2 is negative, then you have to evaluate n using two different criteria, and you have to choose the smaller number. Okay, that is something critical. So the smaller number or smaller factor of safety always dictates the factor of safety for the whole material. Okay, so that is how we calculate the factor of safety. Now, it only means factor of safety if the n value is greater than 1. If the n value is less than 1, there is no factor of safety. It means that the material is going to fail. Okay, so that is how you determine whether a material is going to fail or not. If n is greater than 1, it will probably survive. Okay, and how easily it will survive depends on how much n is greater than 1. But if it is less than 1, it is very likely that the material will fail by fracture. Okay, so that is how the maximum principal stress theory is defined for brittle materials. Now, we can try to put this as a graphical representation. Okay, here one thing I want to note is that these axes sigma 1 and sigma 2, okay, are just the principal stresses sigma 1 and sigma 2. They are not ordered. Okay, so if you think of a 2D stress state where sigma 3 is 0 and sigma 1 and sigma 2 are essentially the free variables in some sense, the free principal stresses, then if you plot the failure envelope of a brittle material, it essentially looks like a square. Okay. Okay. Of course, the square is not centered at the origin, it is offset, and we'll look at a reason why that is the case. Okay. So what do I mean by this failure envelope? Okay. What I mean by that is that if your stress state is such that you are inside the square, that point will not fail. That point will not have a fracture. Okay, so what you're doing is that you look at every point in the material, and for every point in the material, you can calculate sigma 1 and sigma 2. Okay, and plot that sigma 1 and sigma 2 on this graph. If the plotted point is within this particular square here, the material will not fail. Okay, if it is outside, then the failure will initiate from that point. Okay, and why do you have this graph? The reason is quite simple. Okay, so if you think of a case, okay, where sigma 1 and sigma 2 are both positive. Okay, again, we are not ordering them as principal stress number 1 is sigma 1 and sigma 2. These are just the two principal stresses, right? If the principal stresses are sigma 1 and sigma 2, and they are both less than SUT, this value. Okay, essentially that means that the material is not going to fail. So anywhere within this square, it is not going to fail. But the moment say sigma 1 exceeds SUT, so you're somewhere here, then you're outside the envelope, then it's going to fail. Okay? So essentially, as long as sigma 1 and sigma 2 are both positive and neither of them is greater than SUT, you're going to be within this square here and the material is not going to fail. Okay? Now, when you go to the other other three quadrants, right? So this quadrant, if you think about it, sigma 2 is positive. Okay? So what matters is sigma 1. Okay? If sigma 1 becomes more than SUC, then it's going to fail. On the other hand, if sigma 2 becomes greater than SUT, it is going to fail. Okay? So again, I want to kind of make a small distinction here. Here we are not looking at sigma 1 greater than sigma 2. We are just looking at sigma 1 and sigma 2 as two independent variables. Okay? So if sigma 2 becomes greater than 0 or greater than SUT, the material will fail. Or if sigma 1 becomes less than SUC or minus SUC, essentially this region here, the material will fail. Okay? So that is why you have this envelope here. So anything within this region is not going to fail. Anything outside that region is going to fail. Okay? So you can look at a similar explanation for this region and this region. So in this region here, okay, let's call this region A, for example, both sigma 1 and sigma 2 are negative. Okay? But as long as the numerical value or the absolute value doesn't exceed SUC, you are good. Okay? On the other hand, if the absolute value of either sigma 1 or sigma 2 exceeds SUC, then you're in trouble. Okay? So this is good. Okay? Now if you look at this region here, let me use a different color. Let's call this region B. In region B, sigma 1 is positive and sigma 2 is negative. So as long as sigma 1 does not exceed SUT and sigma 2 does not have an absolute value greater than SUC, you're fine. But the moment one of those conditions is violated, the material is going to fail. Okay? So that is the reason why you get this kind of a failure envelope, which is essentially a square for the brittle materials, especially using the MPS theory. Again, I want to emphasize that this is the failure envelope for a brittle material based on the maximum principal stress theory. Okay? There are other theories to predict the failure of brittle materials, and the failure envelopes for those theories will look different. Those we will not be covering in this class. You will essentially learn them in an advanced mechanics class if you take one. Okay? So in this case, we are just going to the simplest theory, which is the MPS theory. Okay? And of course, this can be also extended to the 3D case, where sigma 3 is not necessarily 0. Okay? But of course, if you extend it to the 3D case, then the representation becomes more complicated because you are going to have sigma 1, sigma 2, sigma 3 axis, and then you have to visualize things in 3D. But in principle, the idea remains the same, right? If there is a tensile principal stress at some point, if that exceeds the SUT, then the material will fail. If there is a compressive principal stress at some point, if the magnitude of that compressive principal stress exceeds SUC, the material will fail. So it is as simple as that. Okay? And again, it's very intuitive. So I would ask you to kind of think about it carefully and then make sure that you don't get waylaid by signs here and there. Okay? As long as you physically know what is happening, it should be fairly easy to figure out the factor of safety and also whether a brittle material is going to fracture or not. Okay? With that, I would like to conclude this lecture. In the next lectures, we will look at the failure of ductile materials. Thank you.